Hey everybody, in this video, we are going to go over formation constants. We're going to start with just a definition of what they are, and then we're going to actually go through an example problem to show you how to solve these. So first off, formation constant, as it says on this slide, is when we are taking two ions and we are making a new complex ion. Now, the thing about this is if we look at the formation constants on the right on this table, our KFs, you can see that they are very big numbers, right? Over a million, over a billion, over a trillion, some numbers I can't even pronounce. So what does that actually mean for us in terms of chemistry? Remember, for any K, that's an equilibrium constant, and we write K's products over reactants. So for our example equation we have here, we already have the Kf, the equilibrium formation constant, which is our products divided by our reactants. Remember, these brackets mean molarity, which is moles divided by liters. All right, so with these big numbers, what that means is that our numerator will be very big compared to our denominator, or our products will dominate. By the end of this reaction, when we reach equilibrium, we're basically only going to have products and very few reactants left. And how these problems generally work is that it will ask you, okay, how much of a certain product is left over at equilibrium? So we're going to go over the strategy of how to solve that. So let's look at an example problem here. So you mix 125 milliliters sample of solution that is 0.0117 molar nickel chloride with a 175 milliliter sample of a solution that is 0.250 molar NH3. After the solution reaches equilibrium, what is the concentration of nickel that is remaining? All right, so first off, how would you know this is a equilibrium KF problem, a formation problem? Well, one of the key words is equilibrium, right? So we know we have to use a K because K is our constant for equilibrium. What is the concentration of an ion that remains? Okay, so that's a big clue that you're doing a formation constant problem because that's generally how these problems are written. And also, if you are ever given a table like this, or in the question, if you're actually given a KF, well, that's pretty straightforward that we have to do a KF problem. So the first thing we should do, and this is true in any chemistry problem you're given, write the chemical reaction. So we have nickel chloride plus NH3, and you want to write your state symbols. It's just good practice. That is going to make, well, how do we know what it's going to make? That's when I need this table of KFs, or in the problem, you might actually be told what it makes. But I have a compound that's both nickel and NH3, right? So we can ignore the chlorine, and I know to ignore the chlorine, one, because it's not in my table. Two, I'm looking for a compound that has NH3 in either nickel or chlorine. So NiNH3 6 is our product. I'm going to write that down. And we will just have aqueous chlorine remaining. So now we have to balance it. So we have one NH3 on the left, 6 on the right. Put a 6 right there. 2 chlorines on the left, 1 on the right, 2 over here. All right. So that's our balance reaction. That's really the first step that we want to do. Now, one of the tricks about this problem, well, it's not really a trick, but one of the things you need to know is that in essence, it's a limiting reactant problem. And if you don't remember that, I will include a link to my videos on limiting reactant problems. in the description below. But what a limiting reactant problem means is that one of these reactants will run out first, and that's when the reaction will basically stop. So the second thing you should do, step 2, is really find out what is my limiting reactant, right? So what is my limiting reactant? And to do that, I need to know how many moles of each reactant I am working with. So let's do nickel chloride first. So NiCl2. I have 0.0117 molar nickel chloride. Remember, molar just means moles for liters. So this is really 0.0117 moles for every 1 liter. And I have 0.125 liters of that. How am I getting that 0.125? Well, I have 125 milliliters. There are 1,000 milliliters in 1 liter. So really, I'm just taking that 125 and dividing by 1,000. I multiply these two together because when I do that, liters will cancel out and I'm left in moles. So I'm going to do my calculation right now. So what I'm doing is that I'm doing 0.0117 times 0.125. And the amount of moles I have are 0.00146. 0.00146. Moles of nickel chloride. All right, NH3. Let's do the same thing for NH3. Okay, so I have 0.250 moles for every 1 liter of NH3, and I have 0.175 liters of NH3. I'm doing the same type of math I did before. So to find out how many moles of NH3 I have, it's 0.250 times 0.751. 0.250 times 0.175. That's what I meant to say. It is 0.0438 moles. 0.0438 moles. NH3. All right, so we have to figure out which one runs out first. And just by looking at it, I know nickel chloride is going to run out first. You have 40 times more NH3 than NiCl2, right? And so that's just in abundance. Also, how to do this fast if you're doing it on a test. The question says, what is the concentration of Ni2 that remains? Basically, that is telling you your limiting reactant, right? So that's how you do it faster. But I'm going to write the moles over on the right because I need those for this problem. So NiCl2, I have 0.00146 moles. And for NH3, I have 0.0438 moles of NH3. All right, so let me do some erasing here because now we are actually going to solve for how much nickel we have left over in our problem. And to do that, we're going to use everybody's favorite tool in Gen Chem 1. That's right, we are going to use the ice table, right? Initial change equilibrium. If you don't remember how to use an ice table, I will also link to a video below in the description of how to use an ice table. All right, so let's take a look here. So we have nickel chloride plus 6NH3 goes to nickel NH3 plus 2Cl. And since we're doing a formation, NH3, we're actually going to ignore the Cl. This might seem weird to do, but Cl is actually a spectator ion. It is not part of this formation. It doesn't do any chemistry whatsoever. So when doing a KF problem, if you know what you're making, which we do, NiNH3 only have those as your reactants. All right, so our initial concentration of nickel is 0.00146 moles. Our initial concentration of NH3 is 0.0438 moles. We don't have any NiNH3 yet. We haven't made it yet. All right, now the change. Remember what I said at the beginning of the video. We're going to make nothing but products, which basically means all of our reactants will be used up. And the reactant that runs out first, our limiting reactant, is our nickel. So we can just assume we more or less use all our nickel in this reaction. So the change is actually going to be the amount of nickel we start with. Now, NH3, we have 6 of those. So it's going to be -6 times 0.00146. And NiNH3 is going to be plus 0.00146. Right, so that's the change. You just do minus whatever your limiting reactant is. Don't forget the stoichiometry for NH3. Now at equilibrium. So the way the ice table works, I plus C equals E. You just add the I and C rows to get your equilibrium row. And if you do that, you would say, oh, nickel, there is nothing left at equilibrium. However, in a chemical reaction, that's actually impossible, because if we put 0 in, that means our KF value when we calculate it is basically infinity, or actually it would be undefined. So we can't have that. So it's going to be some small concentration. We have to calculate that. So we're going to put X. We don't know what it is. That's what the problem's asking. But for the other columns, we can do that math. 0.0438 minus 6 times 0.00146. And so let me get my calculator out. And I'm going to do that calculation right now. 0.0438 minus 6 times 0.00146. So at equilibrium, the amount of NH3 we're going to have left is 0.0350. So we have 0.0350. And for NiNH3 is 0.00146. So these are moles. Remember, we're working in moles right now. And now we have to go and write our KF equation. So KF equals products over reactants. So NiNH3 6 divided by, so there's our products, divided by nickel. And that's going to be nickel 2 plus NH3 to the 6th power. Remember, any stoichiometry coefficient becomes a power. And remember at the beginning of the video, I said these brackets are concentration, which is moles divided by liters. So we have moles. Now we have to add how many liters our solution is. And this is where we go back to the problem. You mix 125 milliliters with 175. So that's our volume. We're taking 125 milliliters and we're adding 175 milliliters. That is, our total sample is 300 milliliters, or 0.300 liters. So I'm going to take these mole values and convert them to molarity by dividing by 0.300 liters. Oops, 0.300 liters. So let's take a look at that, do that calculation. But this is a very heavy calculation problem on a lot of topics, as you can see. 0.350 divided by 0.3. So the concentration of NH3 at equilibrium is 0.117 molar. So that is equal to 0.117, oops, draw that 7 better, molar. How about NH3 6? So we're going to take 0.00146 divided by 0.3. That's 0.00487. 0.00487 molar. All right, so I'm going to take these concentrations by E rho, and I'm going to plug them into my KF expression. So my numerator is 0.00487. My Ni2 is X. That's what we're solving for. My NH3 is 0.117 raised to the power of 6. That's equal to KF. So we go back to our table for NiNH3, and we see KF is 2.0 times 10 to the 8. Right? I got that from my table up here. Those are bad looking arrows, but that's what I was trying to draw there. There we go. We're solving for X, so I need to rearrange this equation. I'm going to multiply each side by X to get 0.00487 divided by 0.117 to the power of 6 equals 2.0 times 10 to the 8 multiplied by X. You divide each side by 2.0 times 10 to the 8. And you'll get an equation for X. Let me erase some of this to give myself some more space. So our equation for X is X equals 0.00487 divided by 2.0 times 10 to the 8th multiplied by 0.117 to the power of 6. That should give us our concentration of nickel. So let us do that really quick. Pulling out my calculator. 0.00487 divided by, let me do the denominator first, 0.117 raised to the power of 6. Then I'm going to take that number, multiply by 2.0 times 10 to the 8th. 0.00487 divided by my denominator. Divided by my denominator. So 9.49 times 10 to the 6. X equals 9.49 times 10 to the 6 molar. Remember, it's M because we are dealing with an equilibrium constant, and we're always dealing in concentrations. So that's to the minus 6, not the 6, to the minus 6. Big difference there, right? And yeah, so if we look at that number, right, that's a very small number. It's not 0, but it's an incredibly tiny number. And that's how you solve a formation problem. Just to recap, right? You have to write down the chemical reaction. You have to find out your initial concentrations of your reactants. You have to decide which one is going to be used up first, your limiting reactant. Your change column in your ICE table is that amount of limiting reactant. Don't forget about stoichiometry. Do I plus C equals the E, but your E rho for your limiting reactant is just X, like we have for nickel. Set up your KF equation as we did here, and then solve for X. And X should be your answer. If you have any questions about that, let me know in the comments below. Otherwise, I will see you in the next video.